In this lecture, I'm going to introduce the material in chapter 11 of the textbook Meta-analysis and Measurement Error Models. So these two topics are usually not taught in statistics courses in linguistics and psychology and in psycholinguistics, but I think that they're very important topics that can have a very big impact on one's research agenda. So if you're doing a PhD, for example, it would be very, very useful to do a literature review accompanied with a quantitative meta-analysis. And I'll talk about measurement error and its value later on, the measurement error models and its value later on. So let's start with meta-analysis. Oh, that's a mistake here. I will fix this later. It's chapter 11 of the textbook. So there are meta-analysis has a very long history in data analysis and in statistics, and it has played and continues to play a very important role in medicine because multiple laboratories will carry out the same type of studies in different centers in different countries with different subpopulations. And one of the important things that one can do with that kind of data from multiple labs is to put them all together and create a synthesis, what we call evidence synthesis, that provides much more information than any one study could provide. And so in recognition, of this important role for meta-analysis, there's actually an organization called Cochrane Reviews. I don't actually know how to pronounce this, but I think it's Cochrane or Cochrane, I don't know. But these people, these are a bunch of statisticians who do only one thing, which is to carry out meta-analyses of published work in medicine. And they have also produced a handbook for carrying out these kinds of systematic reviews of interventions. Interventions in medicine refers to, providing medication or treatment of some kind to see whether it has any efficacy or not. So this handbook is actually very valuable also for psychology and linguistics and psycholinguistics. So it's worth studying if you're interested in understanding more details surrounding meta-analysis, because there's a lot more to meta-analysis in terms of choosing which studies to deploy in your meta-analysis and how to decide on the criteria for including certain studies. Because if you're going to look at all the published studies, let's say in language acquisition or something, right? Some studies might not be eligible to be included because they're looking at a different subpopulation. So for example, if you're interested in native speakers data and you have a study from non-native speakers, that's obviously not eligible for the meta-analysis. So there are selection criteria that one can set up, and they discuss all that in the Cochrane handbook, right? So you can take a look at that. And there are, of course, many other books on this. But the basic setup, of the meta-analysis, and I'm going to be talking about random effects meta-analysis primarily because that's the most useful kind, in my opinion, for the kind of work, that we do in cognitive science. The basic statistical model for meta-analysis is very straightforward. It's actually a hierarchical model. It's a linear mixed model with varying intercepts. That's all, right? So here's how this works. So suppose you have n studies that you're using in your meta-analysis, and each study delivers two pieces of information. One piece of information is the effect size, which I'm calling y. So in the nth study's effect size is y. And the second piece of information that study will provide is the standard error, or the estimate of the standard error, right? So this tells you how much measurement error you have on your estimate of the effect. Okay, So these two pieces of information allow us to set up a model where we assume that each of the n studies effect sizes is coming from a Gaussian distribution where the standard deviation um, of the Gaussian distribution that's producing the nth studies estimate is whatever the standard error is. So that's actually part of the data that we are getting from each study. And the underlying effect size in each of those n studies is an unknown latent parameter, which I'll call zeta sub n. So each of the n studies has its own latent parameter value, which represents its true effect size. Okay? So the reason every different study will have its own unique if true unknown effect size is that each study will be done by a different researcher. It will involve different subjects. It will involve different lab protocols, different slight subtle differences in methodology and in the type of machinery used can have a big impact, on the estimates. So all these things come together to have an impact on the estimate from each study, and that's why every study will have a different, in principle, it will have a different effect size. But this is an unknown and unobserved value. Okay, it's a latent parameter. The next assumption we make is that each of those zeta sub n unknown latent values will be also be coming from a Gaussian distribution where the standard deviation represents the between study variation. So that's again a linear mixed model or a hierarchical model, right? It's telling you how much each study varies around some true value, true unknown value for the effect size, and that true unknown value for the effect size is the zeta here. So this is the entire model actually, right? This is a hierarchical model because it has between study variability and also within study variability here. Okay. All right. So usually, what we're interested in is the overall effect size, which is this zeta parameter, which is also a latent parameter. We don't know what it is and we'll never know what it is, right? But we can estimate it through by passing it through the zeta sub n latent parameter. So what this means is we measure the effect sizes and the standard errors in each study. We set up a model for the zeta sub n's, and then in the end, we end up with the following parameters. We have the zeta parameter, we'll get a posterior on that. The tau parameter is going to tell us how much between study variability, what they also call heterogeneity. So how variable are the studies, across labs. That's a measure of that variability. And we'll also get estimates of each study's underlying effect size. So there will be n parameters here for zeta sub n, and then one parameter here and one parameter here. So if you have n studies, you have n plus 2 parameters, okay, in the model. So that's how it works. So what you have to do is you have to, when you're working on a particular problem, research question, you need to have a certain number of studies, to work with to do a meta-analysis. If you have only one or two studies out there in the literature, then obviously a meta-analysis doesn't really make that much sense, right? So you need to have at least, I would say, maybe 5, 6, 7 studies. Usually one has many more. So in one paper where we did a meta-analysis, this one here, so this paper here, we had about 80 or 90 studies, or at least 80 or 90 effect sizes from sometimes multiple effect size estimates from one paper, So that's what we have. So that's quite a substantial amount of data to start with. So usually, when you're doing research, what will happen is that people will have worked on that problem in the past, right? So you will have some prior data to start with, or prior estimates to start with from published papers. From each published paper, you can, even if though you don't have the original data from each study, you can still extract the estimate of the effect size and the standard error estimate, right? That's what you need to get started. So there are also other kinds of meta-analyses which you can read about in a book like this. This is a good book, but it focuses most exclusively on frequentist meta-analysis models, and I will discuss those briefly later on. So, so let's set up a meta-analysis now based on the data in this paper, which was published like 2017 or something. So this is available in the bcogsci package, okay? And so what we're going to do is we are going to load the data and then look at it. And so in this data set, what you're seeing is a phenomenon called similarity-based interference, something I've worked on for like 25 years now. But this is data only from one person's lab, right? So there's a researcher called Julie Van Dyke, and she carried out a whole bunch of studies over many years on similarity-based interference. So we have an effect size in milliseconds. Okay, so this is reading time, the standard error estimates from those effect sizes, and these are study IDs. Okay, they're just arbitrary numbers that I put, and these are the names that we gave to the individual studies. Okay, so these are just names for us so that we know which study we are talking about and which experiment we took the data from and so on. And you can see that we have multiple from the same paper we have multiple estimates. So technically, like these three data points, they're not exactly independent, because they're coming from the same paper, but we're going to treat them as independent because they do in fact involve different subjects. Okay, so this average is from a set of subjects, this average is from another set of subjects. Despite the fact that all the work was done in Julie's lab, one could still roughly assume that these are independent data points. So all these are independent, assumed independent. Okay, all right, so all these estimates, it is pretty tedious to extract them from the papers actually, because sometimes researchers don't report the actual effect size. Sometimes you have to even measure it from the figure, that they show. And like you have to take a ruler and like figure out what the effect size might be roughly, And often you will find, that people don't even provide enough information to figure out the standard error, because they will just tell you if the effect was significant or not, and then you're kind of stuck, and you don't know how to figure out the standard error. But having said that, I mean, you can do some, use some simple knowledge about statistics to figure out the standard error. So for example, if you remember, like the observed t-value, is usually the effect size, and then the null hypothesis value, which is usually 0, divided by the standard error, right? So that's the formula. And so there are three variables here: the observed t-value, the effect size, and the standard error. So if you know an estimate of the effect size and you know what the reported t-value was, you can figure out the standard error, right? Similarly, if somebody gives you an F-score, sometimes you'll get an F-score. One fact about the F-score is that it's the same thing as a t-squared value, right? In a repeated measures design. And so there also, once you know the F-score, you can figure out the t-score. If you know the effect size, you can figure out the standard error. That's how we often get these kinds of estimates. But there are a few rare cases where even that information is not available. And then what one has to do is that one has to do some guesswork by looking at the confidence intervals provided by the researcher. Those are, of course, very inaccurate estimates of estimates, So it gets messy if people don't provide enough information, and they often don't, or sometimes they don't. Okay. Anyway, so you can get all the data, the raw data, and all the other analyses that were done for this paper from this URL here, the short URL that you're seeing here. And if I remember correctly, I might have done the analyses in 2017 using JAGs. I don't remember why I did that, but that's how we did that then. But today I will show you the Stan code for this. Okay. So here's the model again. There's the effect size estimated from each study and the standard error estimated from each study. And we're going to implement this model now. First of all, we're going to implement it in BRMS, then I'll implement it in Stan. So what is all this? Why am I repeating all this information? So basically, I'm just presenting the whole model in one place here. And so there's the effect size, latent zeta n parameter. Zeta n is coming from a normal with zeta and tau as the parameters. And then you have to define priors, but you define priors only on these, right? Because these are parameters too, but the prior on this parameter, on these parameters, is this thing here. And here you also see the detail that the frequentist linear mixed model, which assumes that the intercept and slope adjustments are coming from a normal distribution with a mean 0 and some standard deviation tau, that's a kind of prior even in the frequentist model. So the frequentist linear mixed model is a frequentist model with Bayesian characteristics, because the intercept and slope adjustments basically have a prior specified for them, in a way. So that's the prior here for zeta sub n, but the priors for the principal parameters tau, zeta and tau are given here. And these are just reasonable values on the millisecond scale for the problem that we are studying here. By the way, I just want to mention that it's actually reasonable here, even though this effect size is milliseconds on the millisecond scale, it's actually reasonable to assume that the milliseconds data is coming from a normal distribution. Why is that? Because these are effect estimates of the mean effect estimates, and the sampling distribution of the sample mean is normal asymptotically, right? As n goes to n gets larger and larger, the central limit theorem is in action here. That's why I'm assuming a normal likelihood for the effect sizes, even though those are milliseconds. So I'm not assuming a log normal. It wouldn't make sense here. Okay? And it makes perfect sense to assume normal because of the central limit theorem. Okay. All right, so there that's the model, and now let's implement it in BRMS. So we define the priors as usual for the intercept. The intercept is the zeta parameter, and the standard deviation is the tau parameter. Okay, notice that there is no sigma parameter. I'll just get to that. So the syntax in BRMS is slightly different from what we are familiar with. This is what we are familiar with varying intercepts, so that's the same. So there's only an intercept, and then there's varying intercepts around the grand mean zeta value, So those are the adjustments to the zeta estimate, which represent the deviations around the grand mean. So the zeta sub n's are this thing plus the estimate for the intercept adjustment for each subject. Okay, well, I'll just show you the plot for that later. So here's the data that goes into the model, the effect estimate and the standard error. So you have to write it like this: response standard error, and then standard error in single quotes, and then sigma is set to false because there is no sigma parameter anymore in this model. Okay? You can see that here. There is no sigma parameter. We just have between study variability. Okay. So, and then the priors and then some control parameters to make the model converge. You'll see what happens when we try to, fit this model in Stan for the same data. You will have convergence problems. We will do a non-centered parameterization there. as I discussed in the previous chapter. So you can now extract, once you fit the model, right? Fit SPI, if you extract the short summary. Short summary is a function we wrote, or Bruno wrote, and that's at the beginning of this RMD file. So you can look at that code and use it to extract the short summary, which eliminates some of the noise, in the output. So it's showing you the standard deviation of the intercept. And so this is the tau estimate with a 95% credible interval. This is the population level effect estimate, that is the zeta posterior mean with a 95% credible interval. And sigma will always turn up in this kind of hierarchical model because of the way that BRMS is written, So they can't just remove, they could have removed sigma, but I guess the author of BRMS, Paul Buchner, decided to keep it present, keep the output present, but this is not doing any work here, right? So there are no samples for sigma because it's not a parameter in the model. So this is just kind of a spurious output here, okay? So don't be confused by that. All right, so now, the interesting application of a meta-analysis is that now I have a posterior summary of the effect estimate based on 20 years of work that Julie Van Dyke did. Now that's a very valuable set of data, that's out there. And now I have a statistical summary of that estimate, right? So my 95% credible interval is going from 3 milliseconds to 27 milliseconds, right? And the effect estimate is 13 milliseconds. So what does that mean? That means if the 95% credible interval is going from 3 to 27 milliseconds, let's say 28 to 3 milliseconds, okay, just be a little bit broader, okay? So the width of that interval is 25 milliseconds, okay? So 25 milliseconds, the width of the credible interval is 25 milliseconds. Remember that a credible interval is plus minus 2 times the standard error or standard deviation, right? So if I divide the 25 milliseconds by 4, that gives me the standard deviation of my effect estimate in the posterior. So 6.25 is my standard deviation of this effect estimate, okay? So if I were now doing a future study, when I start doing a future study on similarity-based inference of the type that Julie Van Dyke did, what I can now do is that I can build on her work. I can build on what she learned from all her studies, and by including an informative prior that has mean 13.19 and standard deviation 6.25. I can make it a little bit bigger and make it 7 or something. So let's say 13 and 13 is the mean and 7 is the standard deviation. That is an informative prior that I could plug in into my Bayesian model, and my new data would then be informed by this prior. Very valuable, not only for building up knowledge incrementally, right? Over the years, you can gain more and more information about the phenomenon you're interested in, but even more importantly, if you're doing a Bayes factor analysis, you can do something called a replication Bayes factor. We discussed that in chapter 13 for Bayes factors. You can do a replication Bayes factor. This is something that E.J. Wagenmakers has advocated for, to check whether you have evidence for the effect given the data that you have and given this informative prior. In any case, you might want to know if you take an optimistic position, that the effect size is 13 with standard deviation of 7, then does your data actually support the existence of interference effects? Okay, so that's a very, very useful thing now. Now compare that with the frequentist way of doing things. Every time that you do a study on similarity-based inference, you start from a state of zero knowledge, right? There's no, you can't bring in prior information into your frequentist model. And so what you end up with is every time you do a new study over, let's say, 100 years, you're going to be starting from a state of zero knowledge about that, right? Because you have no priors at all. And so you don't really build up your knowledge explicitly as you collect data. But frequentists do build up their knowledge implicitly, right? So what they will do is they will refer back to previous studies, estimates, or significant effects in previous studies and argue that, oh, look, here I did my similarity based interference study. I got an effect in the predicted direction, and it was statistically significant. And here are all the 50 studies that came before me, out of which, let's say, 40 showed significant effects, So they will do a vote counting of significance most commonly. That's how they will accumulate their knowledge. So it's a very informal way of accumulating knowledge in the frequentist way of thinking. Here is the formal way that you can incorporate your prior knowledge into the into your current data analysis. So very valuable stuff, right? So that's one thing. In this paper, you will see how we accumulate knowledge. We demonstrate in this paper how you can build up your knowledge about a particular problem, which happened to be very controversial in the literature. There was a big drama about this, which I can talk about in the class if you want. But there was a very, very angry exchange between researchers about the existence or non-existence of certain effects in sentence processing, and it got very acrimonious. But you could just objectively build up your knowledge about, what we've learned from the new data given the prior data. So that's a good demonstration of how this works. In another paper that is also now published, we build on Julie's work, actually Julie Van Dyke's work, what I just demonstrated. We build on that explicitly when we carry out a new experiment. So all these methods are not being used, in cognitive science. And that's very surprising to me because all these methods are well known. There's nothing new about them. So they should be completely standard operating procedure, in my opinion, especially in fields, where you're working with babies, for example, and you have sparse data. You can bring in information from previous studies and build on that knowledge. So there's like a many babies project that tries to do that as well, with multiple data sets from different labs. That's also a meta-analysis, basically. So what you can do is, what I did here is I extracted estimates from different studies and I put them together into a random effects meta-analysis model. But if you have access to multiple labs' original data, you can just pool all the data together, okay? Literally put all the data together. You have to be careful to label the subjects, to be unique in each study, because subject 1 in study 1 is not the same subject 1 in study 2. So you have to be careful about that. It's a very common mistake to forget to relabel the subjects, okay? But if you have all the data from all previous studies, like in the Many Babies project, then you can simply put together all the data and just do your model, fit your model, your hierarchical model. That's also meta-analysis. Okay? Now, an extension of the meta-analysis is something called meta-regression, right? Here, what you can do is, instead of just focusing on the effect size, you can look at the effect of predictors on the effect size, okay? So this is not unfamiliar to us. This is just a linear mixed model, a hierarchical model with a slope. That's all there is, Notice that you cannot have varying slopes in this model now because you have only one data point from each study on the effect size along with the standard error estimate. Okay, so you don't have multiple repeated measurements from the same study. So that's the only situation where you can have varying slopes. So there's going to be no varying slopes here, just varying intercepts. So the model is the same. The only difference is I've got this predictor, some predictor in each study, and now I've got a slope parameter that tells me something about the effect of that predictor on the effect size. So there's one more parameter now in the model, beta, and everything else is the same as before. So let's take a look at an example, right? So this is a meta regression on a phenomenon which I must have discussed earlier called agreement attraction. So it's a very famous observation going back to the 1960s or 70s that when people read sentences like or hear sentences like the key to the cabinets are on the table, they think that the sentence is fine, even though the sentence is the key are on the table. It's an ungrammatical sentence, but people think that it's fine. And in fact, I just had a paper reviewed for a journal, and two of the three reviewers actually complained that we had produced a grammatical sentence in the paper, but they wanted to produce the ungrammatical version of that sentence because they felt that this is more grammatical, this kind of construction. So it is so prevalent in native speakers English that people will often get very angry with you, and they will say that the key to the cabinets are on the table is the grammatical version, and saying the key to the cabinets is on the table is actually ungrammatical, even though it's actually grammatical, right? So anyway, so this is called agreement attraction, and what's basically happening intuitively is that the plural marking on the auxiliary verb is kind of being connected to the nearest noun, which people want to be plural as well, even though cabinets is not the subject of R, and in English, the agreement is between the subject and the auxiliary verb, not the noun inside the prepositional clause and the auxiliary verb, right? But people tend to want the adjacent, noun verb pair to be similarly marked. Okay, so that's called agreement attraction. And if you compare this sentence with a sentence like this, where instead of cabinets I have cabinet, people will immediately notice that this is an ungrammatical sentence. Okay? But they will get fooled by this sentence and think that it's just fine. And in fact, in reading term studies, what you'll find is that people read this auxiliary verb faster with cabinets versus the auxiliary verb here preceded by cabinet. They slow down on the R in B compared to A, even though both are equally ungrammatical. Fascinating detail, right? Anyway, so that's the phenomenon. But one interesting thing is that what's happening here is the cabinets, here is called an intervener. It intervenes between the subject and the auxiliary. So this intervener, when it appears between the subject and the auxiliary verb, that's called a retroactive interference setting, right? So whenever the intervener is between the two codependents, that's called retroactive interference. But you can also set up a configuration where the intervener is not intervening between the subject and the auxiliary, but appears to the left of the subject. Okay, so the cabinets that the key are for seem to be very old. Same situation, except the position of cabinets is to the left of key. Okay, that's called a proactive interference setting. This comes from the memory literature in cognitive psychology, right? So in cognitive psychology, what happens is that, can I just write something on my, I'll just use this thing as my, iPad. So basically, if you have in cognitive psychology, they study memory a lot, memory processes. And so if you have one word that has to be memorized and there's a distractor in between the moment of recall, right? So you recall, if you have to recall the word A after having seen a distractor, you will have more difficulty recalling the word A because of the presence of that distractor. So that's called retroactive interference. Okay, and so You can also set up a situation where you have a distractor coming first, then comes A, and then comes the recall moment where you have to recall the word A, and then you suffer interference from the distractor, and that's called proactive interference. So that's where this vocabulary is coming from cognitive psychology. Okay. All right, so those are two settings, okay? Proactive and retroactive interference. So there's a claim in the literature that retroactive interference is much more damaging. It causes more difficulty than proactive interference. Now, difficulty in this case means that the distractor will play a bigger role in causing agreement retraction at the auxiliary verb, which is the moment of recall of the subject. Because when you reach the auxiliary verb, you try to connect it to the subject of the verb, right? So that's the moment of recall. So the prediction in the sentence processing literature is that you will have a greater agreement retraction effect when the distractor intervenes between the subject and the auxiliary. So this is a claim that Julie Van Dyke made, in a paper. And by contrast, when you have a proactive interference setting, the agreement attraction effect should be weaker, right? So the agreement attraction effect should be stronger in retroactive and weaker in proactive. That's the prediction. So you can study this now, okay? So what we can do is I've extracted the data from some published studies, again from Julie Van Dyke's lab, where there were both experiments looking at proactive and retroactive interference. And what we see, if you look at the averages, of the effect type, estimate by interference type, if I just look at the mean estimate, again, these are reading studies and these are differences between means. So what you see is that the agreement attraction effect, which is negative, right? It's a speed up in, so you see a speed up here compared to here. So that's why it's negative. So this agreement, that's called agreement attraction. Okay, that agreement attraction effect shows up in both proactive and retroactive settings. So it's faster here as well compared to here. And interestingly, the proactive effect is actually larger. It's more negative than the retroactive effect, which is the opposite of what one predicted. Okay? Surprising. But that's only because we have very sparse data. Sample sizes were small, so you can get these fluctuations of mean differences, So I tend to think that the theory is probably correct, but it hasn't really been investigated properly. But we can just use the data as an illustration to investigate how much, what we can learn from these studies, whether the interference type, proactive or retroactive, that's my predictor now, can modulate the effect estimate, right? So I have 7 studies for proactive interference and 6 studies for retroactive. Yeah, that's what I'm working with now, 13 studies, okay? So the contrast coding we're setting up is proactive interference has a positive sign, retroactive interference has a negative sign, okay? So on the some contrast coding, and what that means is that if we get a negative sign on the beta parameter, that would mean that this is very confusing, okay? That would mean that the proactive configuration has a bigger, more negative effect. You have to be careful about the fact that we are looking at effects where our effect is actually expected to be negative here, okay? So that's why that's the prediction. So we fit the model, we load the model, do all the pre-processing. So what we see is the effect size, standard error. This is what we'll need for the study, for the meta-analysis. Carry out the meta-regression. How does that work? All that changes is that instead of having just an intercept, I have an intercept and a fixed effect slope now. Okay, so that's the effect of interference type. That's the plus 0.5 minus 0.5 coded predictor here, this guy here. Okay, so So what we get as a result is one extra parameter here, and you see a negative sign on the slope parameter, which tells you that the proactive interference effect is having a larger impact, which is contrary to theoretical predictions. Okay. But the overall interference effect is still negative, which is what theory predicts also. Okay, so what's the 95% credible interval? Yeah, see, it's like a pretty robust effect. And in fact, this effect is one of the few effects in the literature in psycholinguistics that replicates. So you can build a career on agreement attraction effects spanning 40, 50 years, and you will get consistent results, more or less, if you run properly powered studies. Okay. So it's a good topic to focus on if you don't want any unpleasant surprises in your life. So anyway, if you can now plot the meta regression, and you can see the posteriors, that's the overall effect, negative, and you see that the proactive interference effect is more negative, contrary to theory, and that's the standard deviation, the tau estimate. There's quite some variation in the estimates. Yeah. So actually, I say this, but in the Jaeger et al. Study, we had more data, and we did find the expected pattern. So anyway, so that's how the setup works here for meta regression. You can fit the frequentist version of the random effects meta-analysis, not the meta regression, but I mean, of course, you could fit the meta regression too, but this I'm just showing the meta-analysis, random effects meta-analysis. It works when this RMA function in the metaphor package. So the package is called metaphor, METAFOR, sorry. And so there's a random effects meta-analysis function there. You given the effect size as a vector, given the standard errors squared, so the variances, right, as a vector. Specify the method as a restricted expectation maximization. So that just basically means that when you compute the standard deviations, you divide by n minus 1 and not n. Okay. And then the study IDs and the data itself, right? So what you get is a standard, random effects meta-analysis output. You see the tau estimate, right, is 9.1, and you see some measures of heterogeneity. I mean, they do that in the frequentist paradigm. I ignore all this. I don't think about this much, because then they want to do significance tests, etc. I don't want to do any of that. And then we have the effect estimate, which is 12 milliseconds, and we have like a p-value, of course, right, for the estimate. So that effect is statistically significant, right? Right. So, and like one convenient thing with the frequentist setup is that once you fit this model, you can just pass it through something called forest, forest, and this builds a forest plot for you very quickly. It's a standard way to represent the summary of your meta-analysis. So what you're seeing here is the overall effect estimate with the 95% confidence interval and the mean estimate, and you're seeing each of the studies estimates. So one thing that you're seeing here is that the squares are of different sizes. This is a standard way to represent a meta-analysis graphically, and what these squares represent is the uncertainty of the estimates of the each of the studies. In other words, the bigger the square, the more precise the study was, and the more weight it gets in the meta-analysis, right? So this study has a small square. You see the large uncertainty. This study has a very tight credible interval, so it has a bigger square, etc. Right? So it's just representing which studies have better estimates, like more accurate estimates, because the standard error is small, and which studies have very high uncertainty, therefore hard to take seriously. So these large confidence intervals are telling you that the study was measured, the estimate was measured with a lot of uncertainty. So it could be anything, like we have no idea we didn't really learn much from that study. So those would be low power studies. Those would be low powered. These would be high powered, and so on. Okay, so that's one way to summarize the model. In Bayesian settings, we use a different code, which I'll just show you for summarizing the data. We don't use these squares, but you could do that if you wanted to, of course. So one question that you might have is, why did I set sigma equal to false, in the brms syntax, if you remember? In this meta-regression, for example, and in the meta-analysis earlier, we had set sigma equal to false. So what would happen if you set sigma to true? What would happen is the following. Right? So if you set sigma equal to true, what it does is it eliminates the zeta n's from the picture, right? So the zeta n's will no longer show up in the model, and the model is now described directly. The effect estimates from each study are directly represented through a normal distribution with underlying mean zeta, and this is different now. The underlying standard deviation of the effect size is the sum of the two variances between study variance and the standard error squared of each study. If you take the square root of that, you get the standard deviation, because we always represent in STAN and in R, we always talk about the standard deviation, not the variance. Well, that's why I took the square root here. So now the parameters are still zeta and tau, but notice that there is no zeta sub n anymore, right? The reason this works, the way this works is as follows. It's just a fact from statistical theory that if you have two independent random variables x and y, and the means of the two random variables are mu x and mu y, and they have standard deviation sigma x, sigma y, then if you take the sum of those two random variables, create a new random variable, z, then that random variable will have the following form. The mean of that random variable will be the sum of the means. They're independent, right? Sum of the means. And the standard deviation will be this term here. The two standard deviations squared summed up divided by, with the square root on them to get to the standard deviation. This is also what we do when we do a two sample t-test, by the way, right? Same situation there. Okay, so in our case, what this means is that we set up the following scenario. We think of the individual studies estimates as coming from a varying intercept, an intercept adjustment, which has mean 0 and some standard deviation sigma sub n, and we set up the zeta sub n's to be coming from a normal distribution, just like before, with means zeta and between study variability tau. So using the equations I just showed you, the relationship when you have x plus y and you create z, z is now this sum of two terms, that is the zeta sub n's. So the expectation of zeta sub n is zeta, right? So that would be, the expectation would be zeta, and the expectation of u sub n, the adjustments to the intercept, the expectation of u sub n is 0. So the sum of these two random variables will have a mean equal to zeta, because the expectation of this is 0, expectation of this is zeta, therefore 0 plus zeta is zeta. That's how we end up with this derived random variable, the sum of two random variables having mean zeta, and standard deviation being the sum of the two variances, square root of that, right? So this is why the model works like this, okay? So the model can be fit as follows. So you set up this time effect and everything is the same. The only difference is sigma is equal to true. What's going to happen when you fit this model now, right, is that you are not going to get any estimates of zeta sub n. They will just disappear from the picture, right? So I don't see any advantage to that actually, but you can do it, okay? So, but this was just to explain why I have sigma equal to true or false. Okay. All right. So you will see that now what I will get as output is the effect estimate, and I will get the um, sigma estimate, which represents this, the posterior of this star, the between study variability. Okay, it's very confusing because now we are not calling it tau, we're calling it sigma, but the basic principle is the same. Okay, so one other thing you can do, with the Bayesian meta-analysis, the random effects meta-analysis that we did was to build a forest plot, and the forest plot can be very interesting. I won't discuss this code because it's just bookkeeping to produce the ggplot, output. So I'll show you the ggplot output. This is how we generally summarize, random effects meta-analysis. And here, what you're seeing is this is the overall effect estimate, meta-analysis estimate with a 95% credible interval, also the similarity based interference data. And what we do is we generally plot the original estimate with a 95% confidence interval alongside the posterior. So the zeta sub n, posterior for that particular study with a 95% credible interval. And so this is interesting to see because it illustrates the whole property of shrinkage in hierarchical models, right? So what will happen is that so let's look here. Right, so let's just concentrate our mind on this. Here, I've got some prior estimate sorry, not a prior estimate. I've got the estimate from the published study, and this is the posterior on the zeta sub n for that study, right? And you can see that it's slightly shifted closer to the overall meta-analysis estimate. Not much. But by contrast here, if you look at this study with a much wider confidence interval, the the posterior is shifted closer to the meta-analysis estimate, much more, right? So that's shrinkage in action, okay? That happens in hierarchical models. So what's happening is that in this study, we have very tight estimates. The data are very informative. So the posterior is actually largely influenced by the data. Remember that the posterior mean is a weighted sum of the prior mean and the maximum likelihood estimate. So the maximum likelihood estimate is doing all the hard, heavy lifting here, to give us a tight estimate of the posterior. Here, by contrast, the maximum likelihood estimate is very noisy. Okay, so it's weighted low, and therefore the posterior mean is largely determined by the totality of the data and the prior. Okay, so that's why it's shifted towards the grand mean, right? So that's how shrinkage also works. I hope I discussed this in chapter 5. If not, just remind me and I'll talk about this in class. So anyway, shrinkage is in action here, and you can see that. That's a useful way to summarize, which studies are more informative and less informative. So this is just a variation on the squares, The squares are also giving you similar information. These squares, that's an uninformative study. That's a much more informative study. You can see the same setup here. But you can see it visually more clearly in this kind of plot, okay? So that's why we generally prefer this. Now, finally, the Stan versions are easy, okay? Because you already know Stan. The model, the data that will go in the data block is the number of studies, the effect size vector, the standard error vector, and the study ID. Oh, this should have been an array actually. I don't know why this was a vector here. This should have been an array, okay? But it's not harmful apparently. And then what the parameters are, it's the zeta and the tau parameter, constrained to be positive only. And of course, is the vector of zeta sub n's. This is the case when we are fitting the sigma equal to false type of model. And then the model specification is easy. You specify that the effect size, this is literally writing out the mathematical model now, right? The effect size is coming from a normal distribution with zeta sub n is the mean and standard error is the standard deviation, and the zeta sub n's are coming from a normal distribution with mean zeta and between study variability tau, and then you define your tau, zeta and tau priors, and then you're done, right? And remember this log complement of the CDF, right? To constrain the prior for tau to be positive. All right, so fit the model as usual. It's all inside bcog-sci, so you can just extract it. And when you fit the model, you'll discover that there's lots of warnings. Don't ignore those warnings. What this shows, what the source of the problem is, that there's a correlation between zeta and tau posteriors, right? You see the funnel plots again. So easy solution, non-centered parameterization. We first sample from a standard normal, that's zeta sub n, use the standard normal to get back the zeta sub n's by adding zeta to the product of zeta sub n posteriors times tau posteriors, right? So that's how we get to the zeta sub n's now. That's the non-centered parameterization that I discussed earlier, okay? Right, everything else is pretty much the same. The only difference now, remember, is that zeta sub n is now a derived quantity. It's derived from the standard normal. So it's going to turn up in the transform parameters block, okay? And you don't see it here anymore. So we fit the model. So here's what the model looks like. The data is the same as before. What changes is that we have now, instead of in the parameters, we don't have zeta sub n, but we have z, right, or z. And in the transform parameters block, we go from the z and tau and zeta parameters to the zeta sub n's, right? So we derive the zeta sub n's, and then everything else is the same again. You got the effect estimate. What you also have is the standard normal defined for zeta, so that's a prior on the zeta, right? And then you have the prior on zeta. Sorry, I misspoke here. This is the prior on z, okay? Remember this prior, okay? That's the prior on z, standard normal. And then you have the prior on zeta, the prior on tau, just like before, and the actual generative process for the effect estimates is just like before, nothing different, okay? And now the model will converge and the values will be pretty much the same as before, okay? All right, so now you could also parameterize this model in the way that we did with sigma equal to true, okay? So how would you parameterize that in Stan? So this is just what I described earlier, so I won't repeat this. But if you look at the Stan model, it'll be clear how this works. So now what we're going to do is we won't have any zeta sub n's anymore, okay? They're gone. So this data block doesn't change. Here, we don't have zeta sub n. We don't have z either because we don't need it, right? We got zeta and tau and that's it. And then what we do is we define the likelihood. The data are being generated from a normal distribution with mean zeta, and the standard deviation this time is not the standard error, but the sum of the squares of the standard error and the tau square, the sum of the square of the standard error with the square of the tau, and then you take the square root of that, okay? So you end up exactly implementing this model here, right? That's the only change. Now you've lost all the zeta sub n's, so you can't recover them now. And so then you define your priors as before, and then you're done, right? And then once you do that, you get your tau, your zeta and tau estimates, which are the same. They're not going to change. What you don't have is access to the zeta sub n's. So you won't be able to draw this kind of forest plot because you don't have the zeta n's, which are these posteriors, these shrunken posteriors, that shrink towards the grand mean. Okay, so that's pretty much the story with meta-analysis. The next topic I will cover is measurement error models. Now I'm going to talk about measurement error models, which are closely related to the random effects meta-analysis material that I just presented. And so in these models, one important thing that we will take into account is the uncertainty of the estimate that we have from each subject for a particular variable, both in the predictor and in the dependent variable. So this is a very important tool for us because you will often find, let me just show you, you will often find researchers doing something like this. So let's just simulate some data, right? So I just take, let's say, let me take 7 data points, call them X, right? And then the 7 data points independent of the first, right? And then what one would do is just plot these and try to fit a linear model to these data, So, well, 7 maybe is too little, but let's say 10 data points for X and 10 for Y. Maybe this looks easier to see, right? So if you look at these plots, this plot here, right? If you just eyeball this plot, okay? Just eyeball the plot. If I asked you to mentally fit a linear model, I just produced this at random, like I didn't plan this or anything. So if I ask you to produce a trend line, showing the relationship between X and Y, you might be tempted to draw a line that goes like this. It goes like this. So I don't know what the linear model would tell me, but let's see. Y is a function of X, right? So it shows me a slope of minus 6.5, minus 0.65, and is it significant, right? Yeah, it's like close to significant, so it seems tantalizing that there is some relationship between X and Y, but we know that there isn't, right? Because we generated 2 independent random variable samples from 2 independent random variables. So the interesting situation here that can arise in real life data is that this data point could be from one particular subject based on multiple measurements from that subject for the Y variable and for the X variable. So there will be a standard error on the Y direction on that estimate and a standard error on that data point estimate in the X direction, right? And if we try to fit a linear model to this kind of data, we are ignoring that uncertainty. So we're ignoring the measurement error on both the X and Y variables, right? So if I fit an AB line, would this work? I've forgotten if this would work. I haven't done this for a long time. How do I fit this? Sorry, was it like this? A and B. Oh, I see, I see. So I have to do something like that. That I get the summary and I get this 0.04 and minus 0.65. Okay, so I fit an AB line on the plot, right? A equal to 0.4 and B equal to minus 0.65. Does this work? Yeah, right. So you see, this looks really tantalizing, as if there's something there, but we know that there isn't. And so you can easily get these kinds of relationships if you're ignoring the measurement error. So that's what this presentation is about, okay? Or this section of the chapter is about. So the data that we're going to look at is some data from Bruno Niesenbaum's work published in 2018. What he did was for each participant, he measured something called a partial credit unit score using a memory task called an operation span task. Okay, so this is a measure of working memory capacity that psychologists use. And so what we get from each subject is their PCU score with a standard error around it because it's based on multiple measurements. Okay, so we also measure, or he also measured the reading fluency of each subject by um, making them do another experiment, right? Same subjects, but different experiment in which their reading speed is calculated in characters per second in a rapid automatized naming task, right? So I think what one has to do is one has to see letters on the screen one after another and keep naming them as fast as you can, okay? And that um, the reading speed is measured like that or something. I might be wrong about that, but it doesn't matter. We've got some measure of the reading speed and we got some measure of working memory capacity as operationalized by psychologists. So psychologists have argued that operation span task is a good way to, measure capacity. Okay, so what we want to know is there an association between working memory capacity as measured with the PCU scores, measured with some error, and the reading speed, which is also measured with some error, because there are multiple estimates, multiple data points from each subject, so you can calculate the standard error also for that subject, right? So the data look like this. We got the reading speed and we got the standard error on that. We got the mean PCU for each subject. See, each row is one subject. So we have only one data point from each subject for reading speed and PCU, but each of these is measured with some error. Okay, so we're going to take those errors into account. And so if you plot the linear model, it looks a lot like my simulated data that I produced just now. I got very lucky today that I got a negative slope, because it looked really nice. And so this is also the case here. You're seeing a negative slope here, and it looks like it might be significant. In fact, like you can go ahead and fit a standard linear model, and if you look at the posterior, the slope is negative. The credible interval seems like it might actually be negative, If you calculate the posterior probability of the thing being negative, it's almost 95%, Very tantalizing. If you fit a frequentist model, you can do that too. You also get a marginal, well, marginal is pushing it here, but it's common to push 0.10 as a marginal effect, So with a t-value of minus 1.6. So one could say that, yeah, there's some tendency, the mean is going in the right, predicted direction, that the higher the working memory score, the faster the speed, okay? Is that correct? Yeah, right? So that's the expected pattern, I think, as the as the memory capacity goes up, um, people get, is that correct actually? Speed is higher. Speed should be going up actually. So speed is going slightly downward. So that's unexpected. I'm sorry about that. So I think that it's unexpected that speed is going down as capacity is going up. But you could make an argument for that. You could say that, oh, people with higher capacity process stuff more deeply, and therefore, they take longer or something like that. You can always come up with some story. Anyway, doesn't matter. The main point is that we do see some suggestion of an effect here, okay? And the posterior distribution looks like this, it's negative, largely negative. So you could maybe argue that, yeah, there's some evidence for this kind of, reduction in speed as a function of increasing memory capacity. What we're going to do though is we're going to take the standard errors into account, and this is very reminiscent of the linear or of the meta-analysis that we just read. So what we have is an estimate from each subject. These are n subjects. From each subject we have an estimate of their whatever their y variable is, in this case the reading speed, and we have a standard error on that, and there is the equivalent of the zeta n scores from the meta-analysis. This is the true unknown latent reading speed of the subject. And same thing for the PCU scores, which are measured with standard error. There is some true unknown PCU score for that subject. Okay, so that's how this thing is set up, just like the meta-analysis. And so the model that we will fit, the regression model that we'll fit, is on the unknown zeta n equivalent. So this is the unknown true value of the subject's y PCU score, and this is the true unknown value of that particular subject's oh, am I getting confused now? Sorry, reading speed. This is the y variable, this is the x variable. So I've confused everything now, because it could have gone the other way, could have talked about reading speed and capacity, like who knows what is correlated with what and why, causal reasons are very hard to figure out. So what I was trying to say was that y is the reading speed, x is the PCU. So there's some true unknown PCU for each subject, true unknown reading speed for that subject, but what we are measuring is a noisy estimate with some standard error around it, right? So we're going to take these standard errors into account, just like in the meta-analysis. Okay. So here's the regression model, reading speed as a function of PCU scores. So we got an intercept and slope and standard deviation sigma. Okay. So we're going to have, that's the likelihood function. All right, so for the PCU scores, we're going to assume that there is some true unknown, PCU score for the population, and the individual subjects' true unknown PCU scores have some between subject variability. Same setup as the zeta n's, okay? So we're going to set it up like this, that we got the alpha and beta intercept slope parameters, some priors on those. We're going to set up a prior on the chi parameter, which represents the grand mean zeta scores, and we're going to set up the grand mean PCU score, sorry, is what I meant to say. And then we have the standard deviations, which is the residual standard deviation in the likelihood function, and tau represents the between subject variability in the PCU scores. Easy, right? Standard setup. Here's the prior specifications. Now the only new thing here is, here's the intercept, here's the slope, defining priors for those, and the new thing here is mean ME and SDME. This sigma is clear, of course, right? The mean ME and standard deviation ME represent the unknown mean and standard deviation, that is the standard error, of the latent unknown means that generated the underlying PCU means, that is chi and tau. Okay, so we are defining priors on on those latent unknown means. Okay, so the model itself will be fit with sigma equal to true. So remember, we lose all the zeta n's in the meta-analysis, right? If we use sigma equal to true. Similarly, in this case, the equivalent of the zeta n's is the y true and the x true parameters in that represent the unknown latent true values of the dependent and the independent variables. Okay, so so we're going to set sigma equal to true, so we won't be ever modeling the y true and the x true. Okay, so what we are doing is we are modeling the mean reading speed as a function of the mean PCU, each of which is measured with the standard error. So this is the same syntax as in the meta-analysis. This part is the same as in the meta-analysis. This is new. This is for the predictor only. In the predictor, we write ME, measurement error, of the PCU as a with standard error SE. So these variables are part of the data that are going into the model alongside the dependent variable and the independent variable. Okay, and that's the data frame. Remember, in the data frame we had 4 columns containing this, this, and this. Okay, so there we go. Gaussian likelihood priors are defined. So if you look at the output, you get the intercept, the alpha estimate, posterior, and the slope is now 0, exactly 0, between minus 0.01 plus 0.01. And you got a sigma estimate, which is pretty tight, but that is looking very tight, but that's just because it's at 2 decimal places. Probably there's a lot of more decimal points that you could extract if you looked at it properly, you know. So it's not exactly 0.01 with no variation around it. Okay, there's some slight variation. It's just the scaling is such that it's not visible here. Okay, so you can also compute the proportion of samples of the posterior parameter, you know, the slope parameter representing the effect of PCU on reading speed and being negative, and you see that it's much smaller now. Earlier it was almost 95% and now it's down to 62%. The reason it's gone down, did I have a plot of this? Yeah. So if you look at this whole distribution has shifted closer to 0. So it was more negative earlier, now it's shifted closer to 0. And the reason for that is the measurement errors on the y and the x. So this is a much more realistic posterior on the effect of PCU on reading speed. Okay, so very, very important point. And if you look at the plot now, because notice that each data point now comes with a measurement error on the y dimension and on the x dimension. Each of these has that. Okay, and so we're not maybe not showing it for every data point here because it just gets really messy, but it's there. And it's this measurement error that is damping the relationship closer to a more realistic value of 0. Okay, of course it doesn't mean that there is no relationship between PCU and mean response speed. There could be, maybe we just didn't have enough data, or like we just had some strange behavior among the participants, or something went wrong. I mean, there could be a relationship. I'm not saying that there isn't. It's just that these data don't show any evidence for any relationship. In the standard version of this model, we are going to use the non-centered parameterization, right? Because remember I said that sigma equal to true means that we are, no, sorry, that's a different issue. But what we're going to do is, because we would get convergence problems otherwise, we set up a standard normal of the random variable, and then we use that to produce the true unknown x sub n's. That means the true unknown PCU scores, right, for each subject. So that's, and those are assumed to come from a normal distribution too. Um, so these observed scores, these are the ones we're observing. They're coming from a normal distribution where this value for each subject is the true mean, and the standard deviation between the subjects is represented by the standard error, which we get from the data. Okay. All right. So we are also not going to model the y and true latent variable explicitly, but what we are going to do is we're going to say that the observed y values, that is the observed reading speed, is a function of the true unknown PCU scores for each subject. That's the predictor, and some intercept value, right? So there's the intercept and the slope, but the predictor is the true unknown PCU scores, right, that I have here, which I'm getting via the non-centered parameterization. Okay, that's important for the stand model to converge. And just like in the meta-analysis, we have the standard error, the standard deviation being the sum of two random variables here. So that means we are not ever going to model the y and true values, the zeta n equivalents, in this situation. So the data look like this. We are going to measure x with standard error x, y with standard error y, right? So there's four vectors of data that come in along with the number of data points and the number of subjects actually in this case. And then we have the alpha and beta for the regression model. Then we have the sigma for the residual standard deviation. Tau is the between subject variability, right? Here, this guy, which gives us the x and true, right, by transformation, right, from the non-centered parameterization. And then we have the z or the z values, which we'll use to leverage ourselves into getting the x true values. So these will be derived from the z values in the transform parameters block. This is just like in the meta-analysis where we had to do the non-centered parameterization. There's no difference here, okay? And so this is just back transforming to get back to the x true values, and then the x true values are the mean of a normal distribution that produces the observed x PCU values, right? So the PCU values from each subject that we observe with some measurement error. So this is data, and we're assuming that they're coming from a normal distribution with some unknown value for the PCU value for that subject. This is the likelihood function, next one, right? Alpha plus beta times x true. Remember how we derived that in the transform parameters block right here, right? That gives us the y, the observed y, and the observed y is measured with a standard error that goes into this term here, right? Just like the sigma equal to true setting in the meta-analysis. Everything else is now standard. The priors on the z's or the z's, and then on the alpha, beta, chi parameter, sigma parameter, and tau parameter. That's it, okay? All very standard. And then we fit the model, and then what we get back is the alpha and beta posteriors and the sigma posteriors, just like before. And what we see is very similar values to what I had shown you earlier with BRMS. Okay, so that's basically the setup for measurement error models. These are very useful when you have uncertainty on the measurements from each participant. So one thing to take away from this lecture is that you don't want to be fooled by randomness. And this is just a pure random event that this slope looks so tantalizing, because you want to take into account the uncertainty of the measurement on the y dimension, on the x dimension of those variables in order to get a realistic estimate of the relationship between x and y.